Greetings, folks. Well, I've just fed little Miss Muffet, so I'm hoping that we will have a period of peace before she realizes that I'm in here and comes in and demands to get up in my lap and go to sleep. Today in class, we talked about the idea that if you apply a net force to an object and the consequence is that it moves over some distance, and you want to know whether the velocity change is going to be big or small, relatively speaking, as a consequence of this application of this force, if you were to take the force and dot it into the displacement, you would come up with a number. And if the number was big, you would know that the velocity change would be relatively large. And if the number was really small, you would know that the velocity change would be relatively small. We didn't tack down exactly how that relationship would work, though. We didn't figure that out, that in fact it was going to be like v2 minus v1 or v2 squared minus v1 squared. We just said, relatively speaking, the velocity change would be relatively big or relatively small if you did this dot product thing. So basically, what this video is about is a derivation of what's called the work energy theorem. The work energy theorem is the mathematical relationship that actually does tag down how that relationship works. And so you will see how the velocity changes in very specific terms when you do work on a body, when you have a force that's applied over some distance. Anyway, that's what you're about to see, is the derivation of that relationship. There are a lot of ways to figure out how much net work is being done on a system. One of the more obvious ways to just sum up all of the forces and then take that net force and dot it into the displacement. Mathematically, this is the way you would characterize that process. We're going to use this relationship to figure out a net work quantity, and in doing so, or to do it, we're going to end up making some assumptions. One of which is we're going to assume that the force and the displacement are in the same direction. So when we do the dot product and we take the magnitude of F and we multiply it by the magnitude of D, and then we multiply that by the cosine of the angle between the line of F and the line of D. If F and D are in the same direction, the angle is going to be, between the two, is going to be 0 degrees, and the cosine of 0 is 1. And we simply end up with F times D. If we then notice or realize that the net force is just going to end up equaling the mass times the acceleration from Newton's second law, we end up that the net work is going to end up equaling the mass times the acceleration times the displacement. The next bit of trickery that we need to use is to note that if the force is constant, the acceleration will be constant, and we can then use kinematics. And so we could write the acceleration term as v2 minus v1 over t, and we could write the displacement term as the average velocity times time, where average velocity is the sum of the two velocities over the time interval divided by 2. And if we were to put that into our MAD expression here, the m comes down, a comes in like so, d comes in like so, and then just doing the math, you have v2 times v2 is v2 squared minus v1 times v1 is v1 squared, and the cross terms, these are negative, these are positive, so they'll add to 0. The 2 comes out in front, the m stays where it is, and the times cancel out, and you end up with that the net work is going to end up equaling this difference here, 1/2 mv2 squared minus 1/2 mv1 squared. This relationship is called the work energy theorem. And in fact, this term, this 1/2 mv squared term, is considered to be important enough to be given a special name. It's called the kinetic energy of the body at the particular point in time. So it's not uncommon to have people refer to the work energy theorem or express it as the net work equaling the change in the kinetic energy of the body. Put a little differently, what the work energy theorem actually states is that when some net amount of work is done on a body, its kinetic energy will change. Of course, this isn't the way that this is normally derived in a college level class, especially one that it uses calculus. There the idea is that you take the force evaluated over a tiny little differential displacement that's somewhere along the path between where you start and where you end. And you do that you do the dot product between the force and the displacement. And once again, if the force is along the line of the displacement, that dot product is just going to be the mass times the acceleration from Newton's second law times the displacement. And you do that for all the little differential displacements along the path, and then you sum them up. So this integral sign is just a glorified summation sign, or it's just a summation sign for a continuously changing function. You've got to do a little trickery once you get to this point. The m comes out. A is just the change in velocity with time, dv dt. dr can be written via the chain rule as dr dt dt. Notice that you can cancel the dt's out and you're back to having dr, so that's a perfectly reasonable and respectable relationship for a displacement. This is also basically saying if you think dr dt is like a velocity, so you're taking a velocity times a time, that's going to give you a displacement. So this chain rule is perfectly kosher. Once you've executed the chain rule, you can do the thing that mathematicians hate but physicists are perfectly happy to do, and that is divide out the dt's. This is so amazingly unkosher, it just boggles the mind, but you do end up with a relationship that mathematicians would come to through considerably more effort. When the dt's go away, you end up with m times the integral of v dv. And that integral is going to be evaluated between v1 and v2. So the integral of v dv is just v squared over 2 evaluated from v1 to v2. And after you do the evaluation, you end up with the network equaling the change in kinetic energy. Work energy theorem, it's a fairly powerful tool for analyzing problems. Turns out it's not the alpha and the omega though. We're actually going to use this relationship. We're going to manipulate it in ways that I'm hoping you'll find interesting, and we're going to come up with another relationship that's, in my opinion, even easier to use in problem solving, called the modified conservation of energy relationship, and that is probably going to be the approach that you're going to use more often than not. But in any case, you do need to know what the work energy theorem is, and this is it. So have a nice evening.